So in this lecture we are going to discuss about bilinear transformations. This is an important class of conformal mapping, and this is given by W equals to f of z, where f of z is given by az plus b divided by cz plus d, where we demand that AD minus BC is not equals to 0, and this demand will be important because bilinear transformations will form a group, and to do that you need to have an inverse. So this is the definition of a bilinear transformation. Now it has some important property, and the first one is that it is conformal. Well, let's try to check it. If you think that C is 0, then f prime of z will simply be a by d, right? Because C is 0 and you take the derivative of az plus b divided by d, and this will give you that a by d, that is the derivative of this function. And note that this is not 0, so this is conformal. Why? Because this a by d can be verified from here. If C is 0, then AD is not equals to 0, so A by D cannot be 0. So this is conformal. And what if we consider, so this is, let's say, case I or case 1, and this is case number 2, where we say, okay, let's take C not equals to 0, right? So f prime of z would now be just AD minus BC and CZ plus D square. And we see that AD minus BC is not 0 from the definition, so this is good, this is not 0. However, you can think that, okay, if Z is equals to minus D by C, then we get a singularity, right? So that's why this f prime of z will be well defined if, so this is well defined when z is not equals to this d by c. That means z is finite, right? In order to analyze the point z equals to infinity, that is, since we are dealing with the complex plane, we also need to take care of the z equals to infinity point as well. So for analyzing this z is equals to infinity, we make the inverse transformation. That is, we let z tilde is equals to 1 upon z, and if you apply this transformation into the bilinear transformation definition, then you will end up with bz tilde plus a divided by dz tilde plus c, and this is well behaved. So this is well defined or well behaved on z tilde equals to 0, and this z tilde equals to 0 actually correspond to z goes to infinity or z equals to infinity. Okay, and the image of the point, the image of the point z is equals to minus dc is w equals to infinity, right? And this is the thing that will motivate another transformation, that is given by w tilde is equals to 1 upon w. Then we find w tilde to be equals to cz plus d, and this will be az plus b, and the derivative of this, that means this guy over here, this is also not equals to 0 at z is equals to minus d by c, So it follows that w is equals to f of z, that is defined earlier, is also conformal at the derivative should be the derivative of this guy. Okay, sorry, not this one. So it should be az plus b whole square, and it should be some stuff over here. So you can see that this will not be this in the denominator. There is no 0 popping up, so that's why w equals to f of z will be conformal at w tilde equals to 0 as well. So this was the conformal property of this kind of transformation. And now what we are going to do is that we're going to explore some other interesting properties of this bilinear transformation. The second property is known as the decomposition. So this will be the second property, decomposition. Any bilinear transformation, which is actually not a linear transformation, can be decomposed into two linear transformation and an inversion. So any bilinear transformation which is not linear why we are calling which is not linear, because if you see the definition, if I take c to be 0, then this becomes a linear transformation. If I take c not to be 0 and a not to be 0, this becomes a nonlinear. Even if you take a is equals to 0, this will actually yield a nonlinear transformation. So in general, if I take c not to be 0, that will be a non-linear transformation. So that's why we are saying any bilinear transformation which is not linear can be decomposed into two linear transformation and an inversion. Two linear transformation and inversion. What it means is that w equals to az plus b and cz plus d can be written as a by c plus c cz plus d bc minus ad. And what we can do further is that we can decompose this whole thing. This means that this general bilinear transformation can be decomposed into the following three successive transformations. So these are the successive transformation. This is a linear one, so this guy is the linear. This is the inverse. Sorry, it shouldn't. Z2 is 1 upon Z1, so this is an inversion. And W again is AC plus BC minus AD divided by C times Z2, and this is another linear transformation. So that's why we said that it can be thought of as a linear, then an inversion, then another linear transformation. So this is the decomposition of a bilinear transformation. Then bilinear transformations form a group. Forms a group. The idea behind these groups is currently beyond our syllabus, but to make some very brief comments is that if you take two bilinear transformations, let's say this is one bilinear transformation, this is some bilinear transformation, and what you do is that you apply another bilinear transformation on this W. Okay, so bilinear on W will give you another bilinear transformation. And these group properties will ensure that the bilinear transformations will have an identity and an inverse as well. So a bilinear transformation that forms a group can be written as f of, let's say this one is 2, this one is 1, like this. Okay, so you can think of it as, let's say f1 of z is given by this a1 z plus b, c1 z plus d. Then f of 2, if it is given by, let's say, a2 z, and what is z, we will come back to that, z plus b, then c2 z plus d, sorry, it should be b1 d1 b2 d2. Now instead of these z's, what you need to do right now is that it will take f1 of z as its argument. So let's call this z primes, and z prime will be just f1 of z, which is given by az plus b1 divided by c1z, sorry, a1, and there will be a d1, like this. So instead of the z primes, you now put these things together and you should get another form like this. This is f2 f1 of z, and you should get some a3 that will come in terms of a2 and a1, z plus b3 c3z plus d3, like this. And they also have existence and inverses as well, and that also motivates to represent bilinear transformations with matrices. And from those matrices one can again get an inversion and linear transformation that we saw earlier as well, but we will not dive into that since the idea of group lies behind this course. Now the next property is that the cross ratio of 4 point under bilinear transformation is an invariant. So the cross ratio of 4 points under bilinear transformation is invariant. What it means is that this ratio given by, let me write down the formula first. Z1 minus Z4, and then we have Z3 minus Z2, then we have this similar thing, Z1 minus Z4, sorry, it should be Z1 minus Z2, and here it should be W1 minus W2, 3 minus 4, like this. This ratio under any bilinear transformation will be invariant, and this can be proved by first saying that, so this is a sketch of the proof. What you do is that you take this W1 and W2 that are coming out of some bilinear transformations, and you take their difference, and the difference is simply AD minus BC times Z1 minus Z2 divided by CZ1 plus D CZ2 plus D. This is pretty simple. You just put W1 as AZ1 plus B CZ1 plus D, similarly for W2, and then you take the difference. And if you manipulate this thing with this W3 W2 and W3 W4, you can end up getting this result. This is very easy to show. Or what you can do is that you can do a brute force thing, that first find W1 minus W2. Oops, it should be W1 minus W4 over here. Yes. And similarly for all the products, and then you can finally have this guy over here, because it's pretty easy to see that for any of these differences you see that there is 1 and 2 over here, right? So all the A's and B's, they're the same thing. So the only thing that is changing is the indexes of these Z's, right? So for this guy W1 minus W4, on the numerator you have a Z1 minus Z4, and on the denominator you have this kind of things, but with a Z that will equal to a Z1 on the first quantity and Z4 on the second quantity, and then you have 3 2. So it's 1 4 3 and 2. Similarly you will have a 3 4 and 1 2, and all the denominators will cancel out. So if you want to see that properly, let me just try to show you that W1 minus W4, W3 minus W2 divided by W1 minus W2, W3 minus W4, and if I use this thing as an example, this is AD minus BC, Z1 minus Z2, then this guy will have another AD minus BC, but here we will have a Z3 minus Z2, and it will be divided by what? It will be divided by C Z1 plus D, and then C Z4 plus D. Okay, it shouldn't be 2, it should be 4 over here. Yes. And similarly you have CZ3 plus D, CZ2 plus D, right? And on the denominator of this very big expression, let me go down a bit. Yeah, so on the denominator again you have this AD minus BC. Now you have 1 and 2, so it should be Z1 minus Z2. Then you have this AD minus BC again. You have 3 4, so you have Z3 minus Z4. And on the denominator you just have CZ1 plus D, CZ2 plus D, CZ3 plus D, and finally you have CZ4 plus D. And these two denominators, they cancel each other out. This guy cancels out this guy, this guy cancels out this guy, and you have the ratio. So that's the proof. And what you can do is that if I give you 3 points, you can use this cross ratio and find out the 4th point, and so on. Okay, so now what we want to do is that we want to discuss another type of property that bilinear transformation shows, that is, okay, what is the number? Yeah, this should be the 4th property. So bilinear transformations maps circles into lines and lines into circles. How? Let's see. So this is more of a proof. So if you have a line that is given by this equation, where A, B, C are real numbers, and this line can lie on the complex plane as well, and what you can do right now is that you can use this expression for x and y. Is that right? Yeah, okay. You can use these expressions and you can plug them over here, and what you get is the following. If you use them and plug them inside, you should get an expression like this. Equals to 0, where b is given by this. This is a very fairly simple algebra, so you can do it pretty easily. Now this is still a equation of a line. Equation of a line. Now remember what bilinear transformation does. Bilinear transformation can be linear, and it can also be an inverse transformation. How? So let's go back to the definition. It can be linear if c is equals to 0. It can be an inverse transformation if d is equals to 0 and a is equals to 0. So that would yield an inverse transformation. So that's why it can be thought that at first that we are not using bilinear transformations to prove it, but eventually we are. It's just a portion of that bilinear transformation, because in bilinear you have one linear transformation, then an inversion, then another linear transformation. So now what you do is that you use a inverse transformation. Why? We'll come back to that a little bit later. Is that you use this kind of inverse transformations for z. So these are the inverse transformations, and if you do that, this equation, let's call it equation 1 becomes c w w bar plus b bar w plus b w bar equals to 0. But is this a equation of a circle? Because this is definitely not a line anymore. So what is this? It is a circle. How we can show that? Well, remember that any circle with its origin on the complex plane at some complex number z0 is given by this, and this is the modulus, so this can be written as this, right? We can write it like this. Okay, so now if you just multiply things out, that means you multiply these two guys and you will get zz bar plus b bar of z plus bz bar plus c equals to 0, where b is equals to minus z0 and c is given by modulus of b square, that means z0 square minus rho square, like this. Okay, and if this is the equation of a circle, what is this? If you compare it, this is also equation of a circle. Alright, and in this case our equation, that is this one is showing a behavior where c equals to 0. So what does that mean? That means modulus of b square is equals to rho square, right? It's just indicating what is the radius, and the circle is actually going through the origin. So that's about it, and from this property you can actually show that the inversion maps the interior of the unit circle on the z plane to the exterior of the unit circle in the w plane with some specific conditions, but we'll probably see that in a homework problem. Then I think we are on now on the 7th. This was another property, I think I forgot to mark it. Okay, so let's not give numbers anymore since I'm losing track of it. So another property is that bilinear transformations map inverse points that are inverse points of a circle to another inverse point. So bilinear transformations maps inverse points of a circle it should not be called of a circle, rather with respect to a circle. So let's just be precise over here. With respect to a circle, to inverse points. I'm not going to show you the full algebraic proof because it's a bit long. What I can do is that I can give you a geometrical idea of what this means. So let's say this is a circle, and let's say this is the center Z0, and this point over here, let's say point P, this is one of the inverse points of a circle, and let's say this Q, this is another inverse point. So what are these inverse points? The points that we're calling inverse points, that is P and Q, they're inverse with respect to the circle of this radius. Let's say the radius is some rho, this is rho, and let's say this distance is r. Okay, so this P and Q are called inverse with respect to the circle of radius rho and center Z0 if this Z0, P and Q, they lie on the same line and in this order. And there is another condition that says that, so let me just write down the first condition, that this is for inverse points. First of all, this Z0, P, Q lie on the same line, and the second one is that the distances, okay, the distances, this Z0 minus P or P minus Z0, since this is a distance, order doesn't matter, this condition for the distance is satisfied. So this is some high school geometry, that is the inverse points, that you take the distance, this guy, let's say this is small r, you take this distance, let's say capital R, then capital R times small r is equals to the square of the radius of that circle. In that case, they will be called a inverse point with each other. This P and Q, they are called inverse points with respect to this circle, and they are inverse to each other. So bilinear transformation maps these inverse points to inverse points. Okay, so this is a property. We are not going to touch much details because the algebraic proof is very long. And the last thing that I want to finish it is that a bilinear transformation is the only univalent function that maps any distance which is equal or less to infinity into a similar kind of region. So this is the last thing that, and this is in fact a theorem that tells you that the bilinear transformation is the only univalent function that maps modulus of z equal less than infinity to a region where modulus of w is also equal less than infinity. And this transformation is actually pretty important because you can literally solve problems of fluid mechanics or electrostatic theory with some conformal or bilinear transformation that takes one kind of region to a convenient region where you can do the calculations pretty easily, and we will try to see some of that in our homework exercises. So this will be it for today, and from the next lecture we will touch upon the final topics of this course that will involve some asymptotic evaluation of integrals. So this will be it, and thank you.